All right, chapter 4 is going to be about reactions. We're going to spend most of the remainder of the semester talking about reactions that carbon does, and the chemistry of carbon. Like I said, carbon can do a lot. So we're going to start off our discussion about the addition of HX to alkenes. And chapter 4 is about alkenes, alkynes. And then in each chapter is going to be about a different functional group, about the chemistry of carbon with that functional group. So next chapter, I believe, is about aromatic compounds, and then we'll talk about alcohols in a different chapter, and then aldehydes, ketones, and carboxylic acids, and so forth and so on. But what we'll talk about is HX to alkenes. And whenever I say X in organic chemistry, we've talked about this, but just to remind you, that means either fluorine, chlorine, or bromine. Right? X is kind of a shorthand way of talking about halogens. And iodine. We've got iodine in there. Okay. Now, typically we don't talk about fluorine. HF is considered a weak acid. It's actually not very reactive on carbon itself. So we don't really use it that often when we talk about when we're doing organic reactions. So mainly, if I do say X, it's implying either chlorine or bromine or iodine. So it's either HCl or it's HBr or it's HI. All right, those are the three main acids that we mainly talk about. All right, so this reaction we talked about at the end of chapter 3. It's where you take a double bond and you add an acid to it. So let's use HCl in this case. All right, now remember, there are lone pairs around the chlorine. All right, I'm going to stop writing them because it does take time to do that. And at this point, we know that there are 3 lone pairs around chlorine, or any halogen. All right, first thing we always do is determine what your Lewis base and Lewis acid is. HCl is a strong acid. That's our Lewis acid, or the electrophile. So that means the pi bond in the carbon-carbon bond, that's going to be our Lewis base, or our nucleophile. All right? So what we learned is that the pi bond grabs the proton, because that has the partial positive charge, and these electrons will go in the chlorine, and you form this intermediate. We learned it's called a carbocation. We learned much more about it in this chapter. And we form a chlorine atom. A chloride ion, not a chlorine atom. They are different. There's your chloride ion, and then the second step is now your chloride ion is your Lewis base, or your nucleophile, and your carbon, since it's a positive charge, is your electrophile. So the chlorine now comes in, adds into there, and we have just formed an alkyl halide, in particular ethyl chloride. So the reaction, basically what the reaction is you're converting an alkene into an alkyl halide. So we changed the functional group on the compound. All right, this is a type of an addition reaction. We're adding HCl to it. Okay? So again, we talked about this mechanism. We went over the energy profile from last chapter. So we've talked a lot about it. We're going to go a little bit more into it right now. All right, let's take another example. Let's take methylcyclohexene. And let's say HBr this time. It doesn't matter what my X is. The reaction is the same. It doesn't matter what Br is. That's why I say HX, because X could be anything, bromine, chlorine, or iodine. All right? And we're going to add HBr. Basically what we're doing is adding a hydrogen to one of the carbons and a bromine to the other carbon. And we're getting rid of the double bond. That's basically the reaction. Now, if you notice, in this reaction, there are 2 possible products. I can either add the H to the carbon that has the methyl group, or I can add the bromine to the carbon that has the methyl group. So there are 2 possible products. One product is where I have my methyl, and then the hydrogen added at this carbon, and then the bromine added here. Or the other possibility is the reverse, where the bromine adds to the carbon where the methyl is, and the hydrogen adds to the other carbon. There are 2 possibilities. However, only one of them actually forms. Or, to be more correct, one of them forms in a much larger yield. You probably get a mixture, like an 80% mixture. And the major product, we'll call it the major product, is the one where the bromine is connected to the carbon that has the methyl group on it. And this is the minor product. But for our sake, for our class, we're going to say that this is the compound that forms. Okay? So the question is, why? We always have to ask why. Why is that the case? Well, in organic chemistry, everything is about stability. Okay, if there's one thing that you should have learned by now, what's the most stable? Why is it the most stable? That is the common why question in everything in organic chemistry. So it's the orientation of alkenes is the next topic. Well, it's still part of 4.1. And something called Markovnikov's rule. Markovnikov's rule. At this point, I'm going to call it Mark's rule, because it is a lot easier to say the word Mark than it is Markovnikov. Even though it is fun to say Markovnikov, we're going to just call it Mark's rule. And it's something called a regiospecific reaction. All right, and the name kind of tells you what it is. There's a specific region that your compounds add. Okay, basically, a regiospecific reaction is when only one of many possible compounds form. Right? When only one of many possible compounds can form. So if you're doing a reaction, in this case, there's two possible products that can form. All right? So when only one of them form, that means it's very regiospecific. I'm adding HBr. So either the H and then the Br act like this, okay? Or, like we saw, the other possibility is where the bromine is up here and the hydrogen's here, and the bromine adds to that carbon and the hydrogen adds to this one. And as we saw, this is the major product. That's very regiospecific. It's specifically adding to this particular region. Okay. So, like I said, the question is why? Well, what Markovnikov's rule is, first of all, I did not define it, but what Markovnikov's rule is, Mark's rule, is the halogen bonds to the more substituted carbon. Right? Another way of looking at it is the hydrogen bonds to the, what do you think it is? If the halogen bonds to the more substituted, that means the hydrogen is bonding to the what? To the least substituted. Okay, it depends on where you want to look at it. If you want to look at the halogen's point of view or the hydrogen's point of view. All right, notice, so remember, this is our product. Let me show you. CH3, there's bromine, and there's hydrogen. All right, notice this carbon right here initially had this carbon attached to it, this carbon attached to it, and this carbon attached to it. So it had three carbons attached to it. This carbon, here, let's look at the starting material. All right, so we're looking at carbon 1. There's one carbon, there's a second carbon, and here's the third carbon. So carbon 1 has three carbons attached to it. This carbon right here, let's call this carbon 2, has one carbon, two carbons. The other bond, remember, is a hydrogen. It's not shown, you just have to remember there's a hydrogen. So that carbon only has two carbons. Okay? So technically this carbon is going to become a tertiary carbon. That's why we learned what the difference between tertiary, secondary, and primary are. This carbon starts out as a secondary carbon, or becomes a secondary carbon. Okay? So since tertiary is more substituted, that's where your bromine goes. This carbon is least substituted, that is where the hydrogen is going. Okay? So the all-important rule, why? All right, I'm adding this, I'm including this in 4.1 because it's a perfect transition. And that is because of something called carbocation stability. Carbocation stability. There are several different types of carbocations we're going to talk about, but for right now, we're going to talk about four of them. This is called a methyl carbocation. Because it's a methyl group. Technically, it's carbon with 3 hydrogens, so it's like a methyl group. This one, I'll put an R group. Remember, R means some sort of carbon group. All right, it just is carbons and hydrogens. There's no oxygens, there's no nitrogens. Could be one carbon, it could be a trillion carbons. But the point is that this central carbon is attached to at least one more carbon. This is a primary carbocation. And then we have a secondary carbocation. Finally, we have tertiary. We will talk about some more of them. But for right now, let's just talk about these 4. All right? And basically how stability works is the more substituted carbocation is the most stable. It's very simple. The more substituted the carbocation, the more stable. Okay? So that means the tertiary is the greatest stability, then the secondary, then the primary, then the methyl. Okay? So the tertiary, most stable. That means it wants to form. Methyl, as you go to methyl, least stable, that means it does not want to form. Okay? So, going back to our example, you always have to look at the mechanism. So, when my pi bond grabs the hydrogen can go in 2 spots. Let's say the hydrogen goes to where the methyl is. We form a carbocation at that carbon. Let's say the pi bond. Now, it's not like the molecule knows. It's not like the molecule says, well, I'm going to add here because it's more stable. It just does what it does, all right? But when it forms a product, that product either reacts or it goes back to starting material. So this time hydrogen is going to this carbon. Here the hydrogen is going to this carbon. All right? Notice this is a secondary carbocation. This is a tertiary carbocation. Let's review that because I know sometimes you're still learning even what those are. But so I'm looking at this carbon right here. This carbon is attached to one carbon, and it's attached to a second carbon. It's attached to 2 carbons, that's why it's secondary. This carbon right here is attached to 1 carbon, 2 carbons, 3 carbons, tertiary. So this intermediate is more stable. So that's the intermediate that's going to form, which then leads to the product. Because once you form that more stable intermediate, once you formed that carbocation, your bromine now can easily add into there to form the product. So whatever carbocation you form, that's what leads to the product. And that's basically what Markovnikov's rule is. That's what regiospecific reaction is. And this is the reason why, because of carbocation stability.